Tonight, we're turning our gaze toward the star that never sleeps, our sun. We'll explore why it never stops shining, what truly fuels its endless glow, and how gravity and heat work together to keep it burning softly, steadily, and without rest for billions of years. You'll learn why the sun's light isn't a flame, but a balance, a cosmic heartbeat made of fusion and patience. We'll travel from the blazing heart of its core to the gentle warmth that reaches your skin, and discover why every sunrise feels so inevitable. Now, take a slow breath. Let your thoughts settle, and your curiosity wake. The night may be dark where you are, but somewhere above, the sun is still shining, calm, eternal, and waiting for us to begin. Imagine standing around a campfire at dusk. The crackle, the orange tongues of flame, the smell of smoke. That scene is so familiar that when people talk about the sun burning, it's an easy mental image, a giant version of your backyard fire, only much hotter. It's comforting, even poetic, but it's also wrong, and the difference matters. A real fire needs three things: fuel, heat, and oxygen. The logs feed the flame. Oxygen from the air feeds the combustion, and together they release light and heat until the wood is gone or the oxygen runs out. If the sun were a bonfire, consuming hydrogen like logs and oxygen like air, it would exhaust itself in a blink of astronomical time. No oxygen, no logs in the usual sense, and no flames licking at the surface. The sun doesn't burn, it fuses. At the heart of the sun is a different kind of chemistry: nuclear fusion. Down in the core, temperatures reach about 15 million degrees Celsius, and the pressure is unimaginably high, so high that particles are slammed together with incredible force. Under those conditions, hydrogen nuclei, which are just single protons, don't behave like the separate billiard balls you might picture. They're squeezed so tightly and move so fast that they can combine, or fuse, into helium nuclei. When this happens, a tiny bit of mass disappears, not into smoke, but into energy. That's where Einstein's famous equation, E equal mc/2, comes in. The mass that goes missing during fusion is converted directly into energy, light, heat, and the other radiation that keeps Earth warm and makes daytime possible. The remarkable thing is how efficient and patient this process is. The fusion of 4 hydrogen nuclei into one helium nucleus converts about 0.7% of the original mass into energy. That's a tiny fraction of each atom, but multiplied by the sun's enormous mass and by the number of reactions happening every second, it produces an enormous power output, roughly 3.8 × 10 to 26 watts pouring out into space. If that sounds abstract, think of it this way. Every second, the sun converts about 4 million metric tons of matter into energy. That sounds huge, and it is. But compared to the sun's total mass, it's microscopic. That's why the sun has been burning bright for about 4.6 billion years already, and will keep shining for roughly another 5 billion. It's a slow, steady forge, not a frantic blaze. The actual fusion process in the sun is called the proton-proton chain. It's a multi-step dance. 2 protons collide and, via a rare set of events, one transforms into a neutron, forming deuterium, heavy hydrogen, while emitting a positron and a neutrino. That deuterium nucleus then collides with another proton to make helium-3, releasing a gamma ray. Finally, two helium-3 nuclei meet and fuse into helium-4, and two protons are kicked back into the pool to start again. Those gamma rays created down in the core begin their long, random walk outward, bouncing from particle to particle. It can take anywhere from tens of thousands to 1,000,000 years for that energy to finally reach the sun's surface as the visible light we see. Neutrinos, by contrast, hardly ever interact. Most fly straight out into space, and some reach Earth in about 8 minutes, where detectors can catch a few. Those solar neutrinos are like tiny postcards sent from the core telling us fusion is really happening right now. Why does this feel so counterintuitive? Part of it is that we're used to chemical reactions on Earth. Burning wood or gasoline is chemistry, electrons rearranging between atoms, and those reactions are comparatively slow and messy. Nuclear fusion is an entirely different scale. Binding energies inside nuclei are millions of times stronger than chemical bonds. The forces involved are enormous, and the energies released dwarf anything from a campfire. Another reason the idea of fusion is surprising is quantum mechanics. Classically, two positively charged protons should repel each other and never fuse unless they have impossibly high energies. But in the quantum world, particles can tunnel through barriers. Even when the average energy seems insufficient, there's a small probability the protons will get close enough to fuse. Over the astronomical number of particles and collisions in the sun's core, those small probabilities add up to the steady production of energy we rely on. There's a human side to this too. The sun's fusion is patient and kind. It doesn't flare up in a way that would suddenly incinerate us. It doesn't run out in a flash. It converts mass to energy discreetly, grain by grain, sustaining a stable output that allowed life on Earth to evolve. When you feel the warmth of sunlight on your face on a crisp morning, you're feeling the result of those delicate, high-energy interactions from the center of the sun, radiated outward over eons. That distinction, not a fire, but a furnace of nuclear processes, also helps explain why trying to replicate the sun on Earth is so hard. Fusion reactors must recreate extreme temperatures and pressures, or use clever magnetic or inertial tricks to coax light nuclei into fusing. We can make small-scale fusion bursts in labs. Making a controlled, net-energy positive fusion power plant remains one of our greatest engineering challenges. Even so, we are trying to mimic that slow alchemy because of what it promises: abundant energy with far less radioactive waste than fission. So next time someone casually says, "The sun is burning," picture instead a patient forge at the center of the solar system. A dense, humming core where hydrogen atoms are stitched into helium. Mass slips away and becomes light, and quantum quirks let protons overcome their mutual repulsion. It's less dramatic than a wildfire, but far more powerful and far better at keeping us alive for billions of years. Imagine the sun as a giant tug-of-war where neither side gets to win. On one side, gravity, an invisible, relentless hand, is pulling every atom toward the center, trying to squash the whole thing into a smaller, denser ball. On the other side, deep in the core, nuclear fusion acts like a roaring furnace, turning mass into energy and pushing outward with pressure. The secret of the sun's endurance is that those two forces don't fight to the death. They settle into a truce. That truce has a name astronomers like hydrostatic equilibrium. It's a tidy phrase, but the idea is simple and surprisingly human. Think about balancing a book on your head. If you lean too far forward, you correct. If you tilt back, you right yourself. The sun does the same thing, only with temperatures of millions of degrees and forces we can barely imagine. Every layer of the star feels the pull of the layers above and the push from below, and the result is a steady, humming balance that keeps the sun from collapsing or blowing itself apart. Let's make it more personal. Have you ever adjusted a thermostat? When a room gets too warm, the heater turns off. When it gets cold, the heater kicks back in. The sun has its own thermostat built into physics. If fusion in the core gets a little too enthusiastic, it pumps out more energy. That extra energy makes the whole star expand. Imagine the sun taking a breath and ballooning ever so slightly. As it expands, the core cools down just enough that fusion slows. If fusion wanes, gravity takes advantage. It squeezes the core tighter, temperatures rise, and fusion ramps up again. It's a self-correcting system, a cosmic inhale and exhale frozen at the perfect point in between. You can picture it with a simple animation, a cross-section of the sun with arrows inward labeled gravity and arrows outward labeled radiation, pressure, fusion. If either arrow grows, the star shifts until the arrows match again. The important part is that this match isn't instantaneous the way flipping a light switch is. Changes in the sun's core happen over long stretches of time, far longer than a human lifetime. That slow response is why the sun feels so steady to us, because these corrections take place over thousands to millions of years. For all practical purposes, the sun is a reliable, ancient furnace. There's also a comforting human analogy: parenting. When you have a toddler and they start pushing boundaries, you respond, sometimes firmly, sometimes gently, and the kid adjusts. If you overreact, things get out of balance. If you ignore the problem, it grows. The sun's parents are gravity and fusion, and their relationship is neither punitive nor permissive. It's pragmatic. Each time fusion nudges the balance one way, gravity nudges it back. Each time gravity presses too hard, the heat in the core pushes back. That pragmatic give and take is what keeps life-friendly conditions stable here on Earth. Now, don't imagine this truce as permanent in some absolute sense. It's stable while the sun has the fuel to sustain core fusion, mostly hydrogen being converted into helium. Over billions of years, that balance will shift as the composition of the core changes, and eventually the truce will break in dramatic ways. But on human and historical timescales, the agreement is rock solid. As long as the two forces are matched, the sun shines with an astonishing steadiness. No sudden flares of collapse, no unexpected explosions, just reliable light and warmth. So next time you step outside on a sunny day, think about that quiet, relentless negotiation happening 900,000 miles beneath your feet. The sunlight warming your skin is the visible outcome of a finely tuned, self-correcting system. Gravity pulls inward like duty. Fusion pushes outward like the joy of energy released. Together they keep the sun at the perfect point between collapse and runaway expansion. A cosmic truce that makes our days possible. You step deeper now, not into space between the planets, but into the heart of the star itself. Picture the central region of the sun, a place so compact and extreme that nothing we experience on Earth comes close. Temperatures climb to about 15 million degrees Celsius, and the pressure is crushing. Hydrogen there no longer behaves like the gas you cook with. It's a dense, fluid plasma, stripped of electrons, a roiling sea of bare nuclei and free electrons sliding past each other. Think of a packed stadium on a championship night, but with every person replaced by a proton and the roar replaced by random frantic motion. These protons are constantly jostling, slamming into one another, ricocheting, and colliding. Most collisions are just that, collisions. But under that extraordinary temperature and pressure, something strange and tiny begins to happen. Over and over, protons run into one another. Every once in a while, thanks to the rules of quantum mechanics, a pair manages to tunnel through the repulsive barrier that normally keeps them apart and fuse together. Quantum tunneling sounds exotic, but you can imagine it like this. Suppose two people stand on either side of a thick wall, trying to give each other a single coin. Normally, they can't get through. But quantum mechanics allows, with a tiny probability, for the coin to appear on the other side without the wall being breached, as if the coin briefly takes a shortcut through the wall. In the sun's core, protons do something like that. They tunnel through their mutual electromagnetic repulsion and stick together. When they do, a packet of energy is released. Each successful fusion reaction in the sun is staggeringly small on human scales. A micro event in a universe where we usually measure things in kilograms and kilometers. Yet the core is not a handful of particles. It's a vast, crowded workshop where trillions upon trillions of these tiny events happen all the time. The energies from individual fusions add up. Summed over the whole core, they produce an astonishing output. Every second, the sun converts roughly 4 million tons of mass into pure energy. Pause on that number for a second. 4 million tons per second. Sounds like something from science fiction. And yet it's real. Its mass literally vanishing and becoming energy, according to Einstein's famous equivalence, E equals mc/2. Most of that energy slowly migrates outward, eventually escaping as the warm, life-sustaining light and heat that bathes Earth. But when you compare 4 million tons to the sun's enormous mass, over 1,000 and 1,000 kilograms, it's tiny. The sun is so massive that losing that much mass each second barely dents it. That tiny fractional loss is the reason the star can continue shining steadily for billions of years. Back in the core, the chemistry of this process isn't hand-wavy magic. It's a chain of events governed by physics. Protons fuse into heavier particles, sometimes forming deuterium and helium nuclei, and at every step, tiny amounts of mass are shed as energy. Most of that energy starts out as high-energy photons, gamma rays, and as those photons scatter and are absorbed and re-emitted across the sun's dense interior, they get downgraded in energy and shuffled slowly outward. That long, random walk of energy can take hundreds of thousands to millions of years, meaning the light we see today began its journey in the core long before human civilization existed. But don't let the long time scales make you forget what's happening at any single instant. The core is restless and relentless. At any given moment, the chance that two particular protons will fuse is tiny, but the number of protons is so enormous that fusion is continuous. Imagine standing in a vast desert during a hailstorm where each hailstone is microscopic. The probability of one particular grain being hit is tiny, but the desert as a whole is hammered constantly. That's the difference between human intuition and astrophysical numbers. Small odds applied to astronomical populations produce steady, huge outcomes. There's also something almost poetic about how fragile the process is at the particle level, yet monumentally robust in aggregate. Each proton-proton fusion is like a single spark. Alone, it doesn't mean much. But millions upon millions of these sparks across the core produce a steady blaze that defines the rhythm of our days and the climate of our planet. It's a reminder that in nature, grand scales often arise from countless minuscule events. For you and me watching from Earth, all of this remains invisible. We don't see protons tunneling or gamma rays being scattered. What we observe is the result of these processes: the sun's steady output, the color and warmth of sunlight, the steady cycle of seasons and life. The core is the engine room, quiet in the sense that it's not explosive, but unimaginably intense in conditions. It doesn't roar, it fuses. That steadiness is crucial. If the sun's fusion were wildly unstable, life on Earth would have a very different story. If you ever feel small standing under a bright midday sky, remember this: your life is bathed in energy that was, a long time ago and far away, generated by tiny quantum events in a place so extreme that the rules of everyday experience break down. The sun's core is where the light begins, a dense, energetic crucible in which protons, pressure, and probability conspire to produce the photons that make the world visible and warm. And because the sun only loses a minute fraction of its mass each second, that process will continue almost unchanged for billions of years more, giving humanity and future species a long stretch of steady daylight to build their stories under. So how does the sun actually turn everyday hydrogen into the steady light we see? It happens through a surprisingly gentle process called the proton-proton chain, a sequence of tiny, patient steps that, together, keep our star shining. Picture a slow dance in a packed room. Individual moves are rare, but because there are so many dancers, the overall motion never stops. Step 1. 2 protons meet. That sounds simple, but protons are positively charged and naturally repel each other, so they need high pressure and high temperature to get close enough. In the sun's core, collisions happen constantly. Occasionally, 2 protons squeeze close enough that one of them changes identity. One proton becomes a neutron through a process governed by the weak force, and the pair becomes a new nucleus called deuterium, a proton-neutron duo. That transformation releases a positron, an antimatter electron, and a neutrino. The positron quickly finds an electron and annihilates, sending out gamma rays. The neutrino, on the other hand, hardly interacts with anything and escapes almost immediately, racing out into space. This first step is the bottleneck. It's rare for any given proton because changing a proton into a neutron involves the weak nuclear force, which is by its nature slow. For you and me, it's strange to think that a single particle might wait billions of years before participating in such a reaction, but that's precisely the sun's advantage. It has an almost unimaginably large supply of protons. Even if one proton fuses only once every so often, the sheer number of them makes the process continuous. Step 2. Once deuterium exists, it's hungry for company. Another proton collides with that deuterium nucleus and fuses to make helium-3, 2 protons, 1 neutron. This step is much quicker than the first. It also releases a high-energy photon, a gamma ray, which begins a long, jostling journey outward through the sun's dense plasma. Step 3. 2 helium-3 nuclei find one another and combine to form helium-4, a stable nucleus of 2 protons and 2 neutrons. And in the process, 2 protons are released back into the pool. That's the neat bookkeeping of the chain. You start with 4 protons and end with a helium-4 nucleus plus 2 leftover protons, and along the way, a bit of mass disappears. That missing mass is converted into energy, according to Einstein's famous E equals mc L2, and that's what ultimately becomes the sunlight and heat bathing Earth. At each of those steps, a little energy is liberated. Some of it is carried away as high-energy photons, some as kinetic energy of particles, and some in the form of neutrinos, the ghostly messengers that barely notice anything they pass through. Those neutrinos are precious to scientists because they escape the core almost immediately and reach us minutes later, providing a direct peek into the nuclear processes at the sun's heart. Light, in contrast, takes a very different route. The gamma rays created inside the core collide, scatter, and get absorbed and re-emitted countless times, gradually losing energy. By the time that radiation finally makes it to the surface and out into space, it's the visible, infrared, and ultraviolet light we recognize. That journey from core to surface can take tens of thousands to 1 million years, the photon's version of slow travel. What I love about the proton-proton chain is how counterintuitive it feels. When you think of fusion, you might expect explosive events, sudden bangs and drama, but the sun's power is the opposite: calm, incremental, and reliable. Imagine a stadium where every second a handful of people stand and clap in sequence. Any single person acting is rare, but because the crowd is enormous, the stadium never falls silent. That's the sun. Almost no proton participates in a fusion on human timescales, but because there are so many, fusion is effectively continuous. Let's put a human scale number on it. The sun fuses about 600 million tons of hydrogen into helium every single second. That seems enormous, and it is. But remember, the sun contains the mass of about 330,000 Earths, so it can afford that steady output for billions of years. Amazingly, of that massive amount of fused matter, roughly 4 million tons per second are converted directly into energy. That energy streams outwards and ultimately warms our planet, drives weather, and powers life through photosynthesis. Those everyday comforts, the light in your kitchen, the warmth on your face on a sunny morning, tie back to these microscopic patient collisions in the sun's core. There's also a quiet elegance to the choreography. The proton-proton chain doesn't require exotic conditions beyond high temperature and pressure. It's the reason stars like our sun, which are relatively modest in size, can burn stably for billions of years. Bigger, hotter stars rely on different fusion pathways, like the carbon-nitrogen-oxygen cycle, but for stars the size of the sun, and smaller, this gentle chain is the main show. On a personal note, every time I imagine the process, I think of baking bread. You don't need a sudden blast of heat to make dough rise. You need the patient, steady action of yeast. Tiny changes repeated over and over until a loaf is transformed. The The sun's core is the same kind of slow alchemy. No fireworks, just patience on an astronomical scale. And because the reactions are distributed throughout a vast volume, the sun's output is remarkably steady. If fusion were a single centralized event, we'd see wild swings. Instead, thousands of fusion events happen every second in every tiny region, smoothing out variations. This is why the sun gives us a consistent cycle of day and night, and why seasons and climates can be so stable over human lifetimes. Finally, remember that every photon of light that reaches us today is the product of this chain, or of a long chain of interactions set in motion by it. Whether you're watching a sunset, sitting by a window with a book, or planting a garden, you're participating in the slow work of countless protons that, over eons, have converted tiny amounts of mass into the energy that makes those moments possible. So that's the proton-proton chain in a nutshell. A sequence of small, often unlikely events. Two protons becoming deuterium. Deuterium joining a proton to make helium-3. Then two helium-3 forming helium-4. Each step releasing a little energy, repeated unimaginably many times. No explosions, no panic. Just countless patient chances adding up to a steady glow. Next, let's follow one of those byproducts, the neutrino, and see what its rapid escape tells us about the sun's hidden core. But producing energy in the core is only the beginning of the story. Imagine a photon being born there, a tiny packet of light created in a nuclear embrace so intense it would melt anything you've ever touched. That photon doesn't sprint straight out into space. Instead, it steps into a dense, boiling crowd of particles and begins what feels like the slowest commute imaginable. Picture a subway car at rush hour. People squeeze in and out. You bounce off shoulders. You change direction a dozen times in a single block. A photon inside the sun does something like that, except the crowd is made of electrons, ions, and nuclei, and the bumps happen millions of times. Each interaction is a chance to scatter, to be absorbed and re-emitted, or to lose a little bit of energy. The path is not a straight line, but a random walk, a series of blind, chaotic jostles that slowly tip the photon's character from fierce to gentle. When a photon is first born in the core, it's a gamma ray, extremely energetic, far beyond the visible light you see. But with every scattering, that energy is diluted. The interactions shift the photon's wavelength, and its color, in the electromagnetic sense, slides from gamma to X-ray, to ultraviolet, to visible and finally infrared. This isn't instantaneous. It's a step-by-step softening, like a piece of music being played increasingly quieter until you can only hear a faint hum. Time here behaves strangely. The distance from the sun's center to its surface is hundreds of thousands of kilometers. But because the mean free path, the distance a photon travels between collisions, is so short in the dense interior, its progress outward is agonizingly slow. Estimates vary, but a photon born in the core can take tens of thousands to even hundreds of thousands of years to diffuse to the surface. That sunlight warming your face right now started its life long before human history as we know it. When you stand in a patch of afternoon sun, you are literally feeling the ancient, smoothed result of a process that took generations of photons a geologic scale of patience. Each scattering event has a story. Sometimes an electron will absorb a photon entirely and later re-emit one at a different energy. Sometimes a photon will nudge an electron and lose some energy in the process. In the dense plasma of the solar interior, electrons are the main agents of these interactions, acting like speed bumps that slow and reshape the photon's journey. Over time, the cumulative effect of countless tiny interactions transforms the raw, violent energy of fusion into the calm, benign light that makes life possible on Earth. That transformation is more than a physical curiosity. It's a powerful way to think about change in general. We often expect big events to produce immediate, obvious outcomes. In the Sun, however, the most dramatic birth, a collision of protons and the release of vast energy, becomes something almost tender by the time it reaches us. The Sun takes its time, sanding away the jagged edges of that violence through patient diffusion. It's as if each spark is instructed to calm down, to become usable warmth, before it's allowed to leave the star. There's a kind of poetry in that patience. You can relate it to moments in your own life, a fast, intense argument that, after days and conversations, turns into understanding, a sudden inspiration that needs months of tinkering before it becomes a finished piece. The Sun models the value of slowing down, of repeated gentle interactions reshaping the raw into the refined. As photons approach the outer layers, two things change. The density drops, so the mean free path lengthens, and the random walk accelerates. And the photons have already lost most of their initial energy, so their wavelengths have settled into the region we call visible and infrared. Near the surface, a photon's last interactions are fewer and farther between. Then, at the photosphere, the Sun's visible surface, conditions finally allow photons to escape directly into space. From that boundary, they fly straight outward at the speed of light, crossing the 150 million kilometers to Earth in about 8 minutes. In that final leg, the Sun's generosity becomes immediate. What took tens of thousands of years to prepare arrives in minutes to warm the skin of whoever steps into its light. Think for a moment of the contrast. A single photon spends millennia trapped in a crowded, thudding interior. But once it makes it to the surface, it spends mere minutes crossing the solar system. That juxtaposition feels almost unfairly dramatic, like watching someone train for years and then complete the final sprint in a flash. The slow internal journey is a hidden prelude to the instant we experience. This long internal odyssey also shapes the Sun's personality. Because energy leaks out so slowly from deep inside, the Sun's output on human timescales is remarkably steady. It buffers and averages the small fluctuations that occur at the core, so the sunshine we see and count on is a smoothed, reliable product. This stability is a direct consequence of photons taking their time, of the star's own kind of stoic patience. If you want to picture the whole process in a single image, imagine the Sun as a giant kitchen where raw, volatile ingredients are slowly transformed into something nourishing. The nuclear reactions are the oven's heat, explosive and intense. The dense interior is the long simmer, where flavors mingle through countless stirs and skims until they're mellow and balanced. The light that reaches your skin is the finished meal, warm, comforting, and safe, far removed from the stove's initial blaze. So next time sunlight slips across your desk or warms your face on a chilly morning, remember that it's the endpoint of a protracted, intimate journey. That soft warmth carries within it a story of countless collisions and conversions, of millennia of quiet work. The sun doesn't let energy rush recklessly into the cosmos. It shepherds each photon, teaches it to be gentle, and only then lets it go. A patient, luminous generosity, reaching across time and space. Imagine holding a pot of soup on the stove. The surface looks calm, a few gentle ripples, maybe a steam swirl rising. Now lift the lid, and you'd find a very different story. The broth is churning, currents collide, pockets of hot liquid rise, and cooler liquid sinks. The sun behaves the same way, except on a scale, and with physics that make a kitchen seem quaint. Underneath the bright face we call the sun, layers stack like the rings of an onion. The inner portion beyond the core is the radiative zone. Here, energy doesn't stream out in a hurry. It shuffles. Photons created deep in the core are absorbed and re-emitted over and over, scattering through dense plasma. It's a slow, patient process. Imagine a message passed down a long chain of people, each reading and then whispering to the next. The energy moves outward, but the path is random and meandering. From our point of view, it's a kind of quiet, disciplined transfer. Calm, ordered, relentless. Farther out, the character changes. Enter the convective zone. This is where the sun acts less like a library and more like a simmering pot. Hot plasma near the bottom of that layer becomes buoyant, rises toward the surface, cools as it gives up heat, then sinks back down to be reheated. These are enormous, slow-moving currents, columns and cells, tens of thousands of kilometers across, turning in ways that would dwarf any storm on Earth. If you've ever watched honey heat and move, or seen steam patterns over a hot pan, you've got a useful mental picture. The motion is gentle in speed, but immense in scale and power. Together, the radiative and convective zones form a kind of energy relay team. The radiative zone handles the patient, diffusion-like transport of energy from the deep core, making sure the rate of escape is regulated. The convective zone takes over closer to the surface, handling bulk transport through motion. The combined effect is beautifully tuned. Just enough energy leaks outward to shine steadily. Not so much that the star falls into chaos. Not so little that it collapses inward. It's like a perfectly adjusted thermostat for a truly cosmic furnace. What we call the surface, the photosphere, is not a hard, visible shell the way a planet has one. Instead, it's a thin, glowing skin above a world of motion. It's the layer where the sun becomes transparent enough for light to escape freely into space, and where those rising and sinking convective currents finally meet the open air. From the photosphere, light streams outward, carrying the history of those interior processes. And yet, compared with the turmoil beneath, the photosphere feels deceptively placid. Granules and sunspots are the small visible signatures of deep, chaotic flows, but they're like pebbles on a vast beach. Here's the bit I find oddly comforting. From where we watch on Earth, all that violent complexity blends into a single steady presence. That perfect sunrise, the one you pull your blanket back for, coffee in hand, maybe a sleepy dog at your feet. is literally the end result of millions of years of radiative shuffling and convective juggling. When light reaches us, the jitter of photons and the motion of plasma have been averaged out to a smooth, comforting glow. It's balanced chaos reduced to a simple promise: daybreak will come. Maybe that's why the sun feels so reliable in our lives. We live within a system where extraordinarily complicated, sometimes turbulent processes are constantly tuned to an equilibrium that makes everyday routines possible. I like to picture that simmering pot beneath a calm surface and remind myself that things can be messy and still deliver something beautiful and dependable. The next time you catch a sunrise, give a moment's thought to the two great acts playing out beneath that glow: the patient light walking of the radiative zone and the slow boiling seas of the convective layer, because together they make the simplest things in life possible. So why does the sun keep going for billions of years instead of blazing out like a bonfire? It helps to think about two qualities that seem contradictory at first. Fusion is both incredibly powerful and, in a way, very stingy. On the powerful side, every time hydrogen fuses into helium in the sun's core, a tiny bit of mass disappears and turns into a huge amount of energy. Einstein's E=mc in action. The proton-proton chain that powers the sun turns roughly 0.7% of the mass of the fused hydrogen into energy. That sounds small, but because CH2 is enormous, even a whisker of mass loss supplies an immense output of light and heat. That's why the sun can bathe planets across 150 million kilometers with enough energy to run climates and life. But here's the stingy part. The sun uses that process at an almost glacial pace. Fusion in the core is not a runaway reaction. It's slow and steady. Protons carry positive charge and repel each other, so for fusion to occur, two of them must get close enough. A condition met only in the extreme pressures and temperatures at the sun's center, and even then the reaction relies on the quirks of quantum mechanics, tunneling, to overcome the barrier. It's intentionally inefficient in the sense of reaction frequency. Only a tiny fraction of proton collisions lead to fusion. The result is a steady, carefully controlled power output rather than a frantic release. Put that together with the size of the fuel tank, and you get the answer. The sun contains an almost unimaginably large reservoir of hydrogen. Even though the core is the only region hot and dense enough for fusion, the total amount available there and nearby is enormous. At the rate the sun is converting hydrogen to helium today, it can remain a stable main sequence star for roughly 10 billion years in total. We're about 4.6 billion years into that span. So, roughly speaking, the sun is about halfway through its calm, middle-aged chapter. A personal metaphor helps this click for me every morning. Think of two people paying for the same apartment. One decides to live at full throttle, paying the rent and bills with lavish nightly parties and daily takeout. Their savings vanish fast. The other treats the budget like a long-term investment, making modest withdrawals and letting the principal sit. The sun is the second person. It's not wasting its hydrogen on flashy bursts. It's a meticulous saver, making tiny withdrawals that add up to 10 billion years of steady light. Or picture two lamps. A spotlight that demands a huge battery drain and lasts an hour, and a low-wattage desk lamp drawing a few drops from a vast reservoir and shining for decades. Fusion is the lamp's bulb, immensely bright for its size, and the sun's core behaves like a tap barely open. That sip-by-sip approach is what stretches its lifespan. There's another reason massive stars don't get this luxury: temperature. Fusion reaction rates are extremely sensitive to how hot the core is. If you increase the core temperature, reactions speed up dramatically. Bigger stars have much hotter cores and therefore burn through their fuel far faster. They're the bonfires and fireworks of the cosmos, spectacular, brilliant, and short-lived. The Sun's particular mass places it in the sweet spot for longevity, heavy enough to fuse hydrogen efficiently, but not so heavy that it burns itself out in a cosmic blink. I like to compare it to cooking. A pressure cooker can make dinner in 20 minutes. High temperature, intense pressure, fast results. A slow cooker feeds you all day and still reaches the same delicious end, but it takes time. The Sun is the slow cooker of stars. Its slower cooking is precisely why ecosystems on Earth have had time to evolve complex life, seasons to cycle, and civilizations to rise and write about the Sun as a steady companion. One thing that often surprises people: efficient in physics doesn't mean fast. Fusion's mass-to-energy conversion efficiency is high compared to burning coal, for example, but the Sun's power output is tuned by the physics of its core, so that it converts only a small portion of its available hydrogen every second. Over billions of years, this tiny, steady conversion yields a colossal total energy output. 1 million tiny, faithful contributions add up. That image of conservation, not wasting, pacing yourself, also ties into how we relate to resources in real life. Whether it's saving money, time, or energy, a restrained, predictable use of a plentiful resource will outlast a frantic splurge. The Sun's behavior reads like a cosmic lesson in long-term planning. Massive reserves plus modest consumption equals endurance. All of this explains why the Sun doesn't run out quickly. But halfway through doesn't mean forever. The slow, patient fusion that makes our days predictable is happening only in the core. Eventually, the core's hydrogen supply dwindles, fusion slows in the center, and the Sun's structure must rearrange itself, a process that leads to a very dramatic change in how the Sun looks and behaves. For now, though, we're beneficiaries of that careful, stingy dance, a lamp sipping from a vast tank, lighting our mornings drop by drop. You look up at the Sun, and it seems so steady, the same golden disk we've always known. But get a little closer, through the eyes of telescopes and spacecraft, and the surface is a roiling magnetic stage. Dark patches bigger than Earth, bright streaks that explode in a heartbeat, and loops of glowing plasma that arch and snap like cosmic guitar strings. Those are the storms on our steady star. Imagine standing on a shoreline watching a storm out at sea. From the beach, the horizon might look wild and dramatic, waves cresting and lightning flashing. But deep underneath the water, the ocean's currents keep moving in ways you don't see. The Sun is similar. The surface and atmosphere are messy and lively, yet the engine at its heart is calm and methodical. That contrast is a comforting truth. The chaos we notice is mostly a skin-deep performance. Let's talk about sunspots first. They're darker only because they're cooler than the surrounding surface, but cooler is relative, still several thousand degrees. Sunspots trace twisted bundles of magnetic field that have punched up from the Sun's interior. Sometimes they linger and slowly move, more like smudges painted across the face of a ball of fire. Other times they rearrange and spawn flares, sudden bright outbursts, that can release energy equivalent to billions of atomic bombs in minutes. When those flares send energy toward Earth, we feel their presence through the aurora curtains, radio hiss, and occasional electronics hiccups. And then there are coronal mass ejections, CMEs, giant bubbles of plasma and magnetic field hurled into space. When one of those hits Earth, it slams into our planet's magnetic shield and squeezes it like a hand around a balloon. Charged particles whoosh down magnetic field lines and light up the upper atmosphere. That's when the polar skies turn into ghostly curtains of green and red. For a lot of people, a strong solar storm is simply a spectacular show, a reason to bundle up and watch the sky. For engineers, it's a reminder to keep satellites safe, operators ready, and power grids monitored. What's important is that these storms are all skin deep when you compare them to the sun's true power source. Deep in the core, hydrogen nuclei fuse into helium in an unimaginably slow, steady process. That fusion is governed by pressures and temperatures so extreme, measurements are indirect and models are king. But the key point is timescale and separation. The core changes on timescales of millions to billions of years, while the surface can change on minutes to weeks. The flares and loops, the sunspots and winds, they dance above the surface and are threaded by magnetic fields that live within the sun's outer layers. They rarely, if ever, tinker with the fusion furnace beneath. There's a personal angle to this that I like to keep in mind. When I was a kid, I'd worry. What if a big flare would dim the sun? Or what if the sun got angry and stopped shining? The reality is wonderfully reassuring. The light that warms your breakfast, grows your plants, and powers photosynthesis on Earth is the result of a slow, reliable process deep inside. The storms can change the mood of the sky and rearrange space weather, but they don't flip the switch on the sun's fundamental output. On human timescales, our star is remarkably stable. That doesn't mean solar storms are harmless. They can upset GPS signals, interfere with HF radio used by pilots and sailors, increase radiation risk for astronauts, and induce currents in power lines during very intense events. Engineers watch the sun the way meteorologists watch hurricanes. They don't stop the storm, but they can forecast impacts and advise precautions. Space agencies and companies now harden satellites, build redundancies, and even plan for temporary shutdowns to protect critical systems when a solar storm is incoming. The solar wind, the continuous stream of charged particles flowing outward, is the quieter, persistent side of the sun's influence. Think of it as a breeze that never stops, only occasionally gusting into a gale during eruptions. It shapes planetary magnetospheres, sculpts comet tails into long streamers, and carries magnetic fields across the solar system. Even at its calmest, the solar wind is constantly talking to Earth's magnetic field, nudging and stirring the plasma in our upper atmosphere. So why does this matter to you? Beyond the headline-making blackouts or breathtaking auroras, this story gives us perspective. It teaches us how a system can be both alive and reliable. The sun's surface may look capricious, but the engine that has held our climate and life in balance for billions of years is ancient and steadfast. When you step outside and feel sunlight on your skin, remember it's the product of a deep, patient physics that isn't swayed by surface tempers. Next, we'll trace how those magnetic dances actually form, how the sun's rotation and internal flows twist magnetic fields into loops, and how those loops lead to the flares and ejections that make space weather what it is. So why doesn't the sun suddenly burn out? Could it just flip a switch and go dark? It's a comforting fear to imagine. One quiet instant and everything changes. But the physics of our star is stubbornly unromantic. With the sun's current mass and structure, there is no hidden off switch, no quick path to darkness. Start with the core, because that's where the action is. Deep inside the sun, under an enormous weight of layers above it, gas is squeezed to pressures and temperatures so high that hydrogen nuclei routinely overcome their mutual repulsion and fuse into helium. That process, the proton-proton chain, releases energy in the form of photons and neutrinos. The photons we eventually see as sunlight start their long random walk out of the interior, but the energy is set free in the core. Those same conditions, pressure, temperature, density, only exist because the sun has the particular mass it does. If you removed too much mass, the core would be cooler and fusion would stop. Add too much, and conditions change in other ways. But absent some cosmic tampering that removes or adds a stellar scale amount of mass instantly, the fusion keeps going. There's also a neat built-in thermostat. Gravity is trying to pull the sun inward. The heat and radiation produced by fusion push outward. The balance between those two forces is called hydrostatic equilibrium, and it's dynamic. If for any reason the rate of fusion in the core began to slow, the core would contract a bit under gravity. That contraction raises the temperature and pressure, which in turn speeds fusion back up. If fusion got temporarily stronger, the core would expand, cool slightly, and slow the reactions. This self-regulating feedback means the sun resists dramatic, sudden changes in brightness or power output. It's not a fragile match waiting to blow. It's more like a slow-breathing furnace that corrects itself. Think in human terms. The change in fusion rate required to dim the sun appreciably would also require changing the core temperature by a substantial fraction. The thermal inertia, the sun's mass, and the time it takes energy to leak out is enormous. Photons created in the core take thousands to millions of years to make their way to the surface because they scatter so frequently on the way out. Neutrinos escape almost immediately, and we detect them as proof that nuclear reactions are happening right now. But the light we see is the result of processes stretched across very long timescales. That's why, over human lifetimes and the span of a few generations, the sun's brightness appears effectively constant. Could something else turn it off? Only an event of catastrophic scale would do it. Remove a huge portion of the sun's mass in an instant, or smash it with a body massive enough to disrupt its internal balance. Neither scenario is remotely plausible in our neighborhood. There are no stars large enough nearby moving fast enough to collide with the sun, and there's no known mechanism in normal stellar evolution that causes immediate shutdown. Rather, the sun's life is measured in billions of years. It has been burning steadily for about 4.6 billion years, and has enough hydrogen to continue in roughly the same mode for several billion more. Over those long stretches, the star's brightness will slowly increase as the core composition shifts from hydrogen to more helium, and the structure subtly readjusts. But that's evolutionary, not abrupt. Because the sun's behavior is governed by the long, patient laws of thermodynamics and gravity, it's useful to picture ourselves as small parts of a much slower clock. Generations are born and die beneath essentially the same sky. Children grow up under light produced by processes that began long before their parents were born. That can feel both humbling and oddly consoling. A sunset you remember from childhood and the sunrise you see this morning are cousins, part of the same steady process heard in the faint ticking of nuclear reactions in the core. If you're someone who worries in the dark, it might comfort you to know there isn't an unseen switch waiting to plunge everything into immediate night. If you are listening in the dark, it may help to know that somewhere beyond the horizon, your star is still working gently on tomorrow. The sun's patience is written in its mass and the physics of its interior. It doesn't do sudden theatrics. Instead, it offers the slow, reliable warmth that life and clocks and calendars are built around. That said, steady doesn't mean unchanging forever. Over millions and then billions of years, the sun will become brighter and hotter, and life on Earth will have to adapt or find other solutions. But those changes are slow enough that ecosystems, human cultures, and technologies have the time to respond, to evolve, innovate, move. The takeaway is practical. On the scale that matters to you and me, the sun is not going to quit. The laws of nature and the sun's current state make an instant shutdown effectively impossible. So tonight, when you look up or when you lie awake thinking about the big questions, you can take a small, solid comfort from that steady, unimprovable fact. The star over our heads is not about to stop keeping time. Fast forward a few billion years. Right now, the sun is cruising along, fuel tank half full, a delicate truce between the outward push of heat from fusion and the inward pull of gravity. But that truce isn't permanent. One day, the hydrogen in the core will run low, and everything changes. Think of the core as a furnace made of hydrogen. As the hydrogen gets used up, the furnace begins to sputter. With less fusion pushing outward, gravity finally gains some ground. The core starts to contract under its own weight. When it squeezes, it heats up. The very same physics that makes a bike pump get hot when you compress air. That rising temperature doesn't immediately restore the old balance. Instead, it ignites a different structure. Hydrogen keeps burning, but now in a shell wrapped around an inert, helium-rich core. That shell burning is surprisingly energetic. It pumps more heat into the outer layers, and those layers respond the way a balloon does when you heat it. They expand. The sun will swell, not by a little, but by a huge factor. Surface layers that are now close and familiar will stretch outward, cooling as they spread. The surface temperature drops, so the color shifts toward red. Our once yellow star becomes a red giant, larger, brighter in total output, and softer in tone. Try to picture that sky. The sun, now bloated, would fill far more of the dome above you if you could be there to see it. An immense, ruddy disk that casts long, warm shadows. Night and day as we know them would be rewritten. But here's the honest part that keeps this moment oddly poetic. No human will witness this transformation. It's so far from now that it belongs more to imagination than to immediate concern. Like the last page of a book you will never reach tonight, our species, or whatever comes after us, will be part of stories and fossils long before that red glow arrives. The red giant phase is dramatic, but not forever. The sun will lose mass through strong stellar winds, shedding outer layers into space. Those expelled layers don't just vanish. They drift outward and eventually form a glowing shell of gas and dust known as a planetary nebula. an oddly delicate name for something that once was the engine of our daylight. At the center of that spectacle, what remains is the sun's core, stripped of its outer blankets, compressed into a dense object about the size of Earth, but containing a large fraction of the sun's mass. This remnant is a white dwarf, a hot, compact ember that no longer produces energy by fusion. It shines because it's still extremely warm, but with no internal furnace to keep it going, it will slowly radiate away its heat. Over billions, and then trillions of years, it will dim, cooling toward darkness. It's a quiet ending compared to the fireworks of more massive stars, but there's a melancholy beauty in it, a concentrated memory of what once was, glowing softly as it fades. It's easy to give these stages a dramatic tone, red giants swelling, planets being engulfed, nebulae blooming, and you should. They are dramatic, but they are also distant, both in space and time. The sun has billions of years left where it will continue doing what it's doing now, fusing hydrogen in its core, providing steady light and warmth. That simple fact makes the distant end of the story feel less like a threat and more like a conclusion written in the language of slow change. There's a comforting symmetry in this cosmic life cycle. Stars begin as diffuse clouds, concentrate into bright, active furnaces, and eventually hand their materials back to the universe in new forms. Even in their endings, they don't stop illuminating the cosmos. They keep shining, sometimes in different colors, sometimes as faint embers, and their remnants seed the next generation of stars and planets. So when you look up at the sun tomorrow, or think about it as you fall asleep tonight, remember, stars do end, but they do not forget to shine along the way. Think about the first thing you notice when you step outside on a clear morning. The warmth on your skin, the way shadows peel away, how colors look a little truer. That sensation is not incidental. It's the sun's steady output, a slow, predictable river of energy that reaches every corner of our planet and sets the stage for everything that happens here. It's easy to take that for granted, to call it background. But that background is the reason we have oceans to walk beside, weather to plan our days around, and the very possibility of life itself. Plants are the most obvious translators of that light. In millions of tiny cells, chlorophyll captures sunlight and, through chemistry that's been tuned over eons, turns it into sugars. Those sugars feed roots and shoots. They feed insects and deer, and through long food chains, they feed us. When you bite into a piece of fruit or smell the sap of a newly felled branch, you are tasting sunlight that was once trapped in a greenhouse of green. Forests grow, deserts remain deserts, and grasslands ripple because of how energy arrives and is used. The sun sets the budget, and ecosystems fill that budget in different ways. But the sun does more than feed mouths. Its steadiness stabilizes climate over the long haul. The fact that the sun's output changes only very slowly gives Earth a kind of thermal patience. Ocean currents can settle into patterns, jet streams can form, and seasonal cycles establish themselves. That long-term consistency is why climates can settle into shapes that allow complex ecosystems to evolve. Not too hot, not too cold, changing enough to drive adaptation, but not so wildly as to wipe everything out every few decades. When we talk about stability, we're talking about the sun's habitual behavior over millions of years. And the mechanism behind all of this is quietly powerful. At the sun's heart, hydrogen atoms are fusing into helium. Each fusion event releases a tiny packet of energy, and taken together across the sun's unfathomable mass, those packets add up to the steady glow we see. You'll never stand at the sun's core, and that's okay. You don't need to. The core does its work regardless, relentless and unfazed, emitting light and heat that begin a journey lasting thousands of years before reaching us. Every warm morning, every thriving forest, every calm evening sky traces back to that slow, patient alchemy. There's an intimacy to that if you let it in. Sitting here, listening to this, you're participating in that chain of energy in a small but meaningful way. The photons that warmed a leaf months ago may have started a chemical cascade that eventually fed a meal you ate or grew timber for a house you live in. Even more directly, the light that hits your eyes has been turned into electrical signals in your brain, and those signals are becoming thoughts. I'm asking you to picture that flow: sunlight, leaf, sugar, life, story. Your attention is a kind of metabolism. You convert the sun's output into ideas and calm. There's a poetic humor to it. The sun doesn't know it has been fueling your story. It doesn't aim to nourish forests or inspire poets, and yet its fusion reactions have been the quiet sponsor of every human endeavor for as long as we've existed. Empires rise and fall, books are written and forgotten, people fall in love and grow old. Underneath all of it, the same star keeps handing out the energy that makes those moments possible. That's humbling and oddly comforting. A cosmic stovetop we all live around, keeping the stew of life simmering. So next time you feel the warmth of a benign morning or watch sunlight scatter through a tree, remember the chain you're part of. The sun's steady output is not just a curiosity, it's the infrastructural miracle of life on Earth. And right now, by turning its light into thought through your listening, you are completing a tiny, beautiful loop that began in a place you will never see, but that shapes everything you do. Now that you know why the sun does not simply burn out, you can set aside the image of a fragile flame at the top of the sky. Imagine instead a steady heart of fusion, patient, balanced, and unimaginably vast. It doesn't panic. It doesn't rush. It converts mass into light at a pace that has been measured and kept for billions of years. Hold that thought for a moment. Picture the sun as a quiet machine of gentle inevitability. Above the clouds and beyond the horizon where your day gave up its last color, there is a calm, constant work going on. Think of its glow not as frantic consumption, but as a kind, deliberate exchange. Heavier stuff becoming light, charged particles whispering into space. It's a rhythm, like a metronome you can't hear, but can trust. That steadiness has weathered storms, cosmic nudges, and entire eras. If the sun can keep on with that slow, perfect job across the deep stretches of time, it can surely outlast tonight's little worries. Let that perspective settle in. The things that keep you awake, the what-ifs, the undone tasks, the small catastrophes with loud imaginations, are real to you, but they are also brief when placed next to the sun's patience. Not to minimize what you feel, but to give it a place, important, relevant, and temporary. Your concerns deserve attention, but they don't need to turn into midnight flames. They can be set on a shelf until morning, because the world and the star that lights it are not fraying at the edges. Breathe with that image. Inhale slowly. Count to 4 in your head. Hold for a gentle 2. Exhale for 6. Let each out-breath be a little cooler than the one before. As you breathe out, imagine a faint easing in your chest, like steam dissipating. With every breath, the edges of your thoughts soften. You are not the only thing burning in the universe, and the sun is not burning in your emergency. It is simply being itself, patient, stable, and reliable. If your mind wants to sprint toward tomorrow's anxieties, picture the sun's surface instead. Not searing chaos, but a simmering quilt of plasma, folding and flowing in slow patterns. Those patterns are fueled by laws of physics so old and so consistent that entire civilizations have been able to map them and build calendars around them. Let that reliability be a soft anchor. Hold on to it like a handrail in the dark, unseen, steady, enough to keep you upright. You might also imagine warmth as gentle rather than consuming. Think of the sun's light as a promise. That energy will continue to arrive, dawn will return, and small tasks will find their time. Tonight's trouble will not extinguish tomorrow's light. Place that promise beside your pillow. Let it be a small, quiet fact you can return to whenever thoughts begin to boil. Slow your breathing again. Inhale, 4. Pause, 2. Exhale, 6. Feel the rhythm of those counts sync with the imagined heartbeat of the sun. Slow, deliberate, wide. Let your thoughts cool in the same way a kettle unwinds from the boil to a soft hum. You don't have to solve anything right now. You can simply be present with the knowledge that the universe keeps its own steady time. The darkness you feel is local, a perspective you carry inward. From out there, the sun's work continues indifferently and kindly, waiting to meet another day. That is not a threat. It is a promise. The source of tomorrow is already stationed far beyond doubt, patient enough to endure millennia, and patient enough to outwait a single sleepless night. Rest into that steadiness. Let your breath slow. Let your thoughts cool. And let the steady light of a distant star be the quiet companion to your sleep. Tomorrow will come, as it always does. For now, let yourself go.